Hello, this is Dimitris Katsimpakis from the University of Basel, and this is a pre-recorded presentation for the Mathematical Psychology Conference in 2020. In this presentation, I will introduce a Bayesian test for context effects that has some desirable statistical properties, and I will present to you the results of a simulation study, as well as a reanalysis from previously published experiments. In the last decade, there has been a development of cognitive models that have formulated different explanations for context effects. Here you can see some examples of that. Nevertheless, in spite of this fruitful development, less attention has been paid on the methodological aspects of context effects. And my goal in this presentation is to make a contribution to this aspect by introducing a robust Bayesian test for these effects. In multi-attribute environments, context effects are frequently measured by having two competing options embedded into two different choice sets. Here, for example, you can see an example of from the domain of risky choice. Here, both gambles yield a specific amount of dollars with some probability. And in this choice set, a third option is introduced, C1, which is similar but inferior to gamble A. Then the same gambles A and B are embedded into another choice set, but here gamble C2 is similar but inferior to gamble B. This is an example of the so-called attraction effect, where participants tend to choose the option that is superior to the inferior option. That is gamble A in the upper choice set and gamble B in the lower set. For this reason, these options are called target options, and the other options are called comparator options. And usually, to measure context effects, researchers calculate what is called the relative choice share of the target, of targets versus the competitor option, while discarding observations in option C. The RST, the relative choice share of the target, is a ratio and is bounded by from 0 to 1, where 50% represents the null hypothesis. In one frequently used version of the RST, the target competitor observations are collapsed into one large set. This, however, ignores potential differences in the number of observations in target competitor choices across the two choice sets. And in the case that the sample size of target competitor observations is unequal across the two choice sets, this RST approach can produce biased results in the direction of the choice with the largest number of observations. In this presentation, I would like to introduce another version of the RST, which is robust to this. And due to some technical reasons, the biased RST version is called unequal weights RST, while the robust RST version is called equal weights RST. Here you can see the structure of the hierarchical model of the two RST approaches. The unequal weights RST, which is the bottom one, estimates, as you can see, a single hierarchical mean for all target competitor observations by discarding the information about the choice set they belong to. The equal weights RST model, top one, estimates two different hierarchical means for the two choice sets independently, and then derives the RST by taking the average of them. Here you can see the result of a simulation we performed with realistic parameter settings of a population to observe the magnitude of the bias of the unequal weights RST model. Here you see two scenarios, one when the alternative hypothesis is true, and here when the null hypothesis is true in a simulated population. The x-axis represents the sample size, target competitor difference between the two choices, while the y-axis represents bias factors in favor of the alternative hypothesis. What you see here is that the unequal weights RST can point to the wrong underlying hypothesis with increasing sample size difference. On the other hand, as you can see here, the equal weights RST remains intact from these changes, remains unaffected, as you can see. And interestingly, this bias of the unequal weights RST exacerbates when the effect size is larger, here, for example, in this scenario, or when the proportion of the target responses are away from 50% in this scenario, which, as you see, the bias is more exacerbated. And this has to do with reasons related to the statistical properties of the binomial distribution. So we showed that indeed in the simulation, the two models can make different inferences depending on the sample size differences across the two choice sets. Nevertheless, we also wanted to verify whether the two approaches make also different inferences in the domain of actual empirical data as well. Therefore, we conducted a bibliographic search to find articles related to context effects where we could apply the two models and see whether their inferences differ. We found 5 published studies, among many others, that adhere to our inclusion criteria, which you can see here. We wanted studies that include the 3 so-called big context effects, namely attraction, similarity, and compromise effects that were within study, within subject design, and that had empirical data or were replication, so excluded modeling studies, modeling only studies. And interestingly, 4 of them used the RST model with the unequal weights RST version. So it would be interesting to see if the results would change. Now, before we have a look at the inferences of the 2 RST models in these 5 studies that we reanalyzed, here you can see the number of target and competitor observations between the 2 choice sets, the differences of that in each study of the 5 and each context effect. This is important to look at because the 2 models make different inferences only when the number of observations is different. Now, as you can see from these empirical densities of relative percentage change in the sample size, the difference is never exactly 0. So it can be distributed around 0, as it's the case, for example, in the attraction effect mostly, or even shifted away from 0, which is sometimes the case with the compromise and similarity effects. Therefore, by looking at this data, we can see that we can expect that the 2 RST models might probably disagree mostly in the compromise and similarity cases, and not so much in the attraction case. Here you can see the posterior distributions of the hierarchical RST means across the 5 studies and the 3 context effects, and also across the 2 RST tests. Now, to do hypothesis testing, we looked both at high density intervals and bias factors. Here you can see the cases where the 2 RST models make different qualitative inferences about context effects. This means, for example, that the HDI of one RST model includes 50%, which is the null hypothesis, while the other does not, or vice versa. Generally, we see that all cases of disagreement are found in similarity and compromise effects, as we expected from before. And also you can see that the HDIs, the high density intervals of the equal weights, tend to include 50% more than the unequal weights test, but not always. Here you can see the cases where bias factors make different inferences. As before, most cases are found in the compromise and similarity effects, but we can also see some cases of disagreement in the attraction effect. Apart from that, we also evaluated whether the different RST methods change the empirical correlations between context effects. Now, these correlations are important because they are predicted by many cognitive models. So here you can see the correlations among the three effects per study and also per RST method. And just by looking at it, I think it's clear that there's not much disagreement um, between the two, the correlations between the two RST methods. And one of the reasons for that is that disagreements in the means of the marginal RST distributions, which we saw from the previous slides, it can happen, still doesn't affect the correlations. Also, it was interesting finally to look at the evidence for the existence of context effects that is provided by the equal weights model that we're proposing in this presentation. And here you can see the shaded areas are the cases where the HDIs include 50%, which is the null hypothesis, according to the equal weights RST model. As you can see, only a few similarity and compromise cases reject the null hypothesis, while most cases strongly support the existence of the attraction effect. So that was based on the HDIs, and you can see here the same analysis, but now based on bias factors. And here you can see that the results mostly agree, but the bias factors is a more conservative procedure than the HDIs, and thus the model provides at least moderate evidence in favor of the alternative hypothesis only for 3 attraction effects and 1 compromise effect cases. So to conclude, we showed that the equal weights RST model is robust to target competitor sample size differences across the 2 sets and in experiments of such design. And we also showed that these differences have important consequences for hypothesis testing, not just in simulated data, but also in actual empirical data. Interestingly, correlations among context effects were similar across the 2 RST tests. And when we reanalyzed the data, the equal weights RST test provided more evidence for the attraction effect and less evidence for similarity and compromise effects. Now, with this contribution, we attempt basically to enlarge the toolbox of statistical tests for researchers in decision making. And also, I hope that I convince you that more attention should be drawn also on methodological aspects of context effects and decision making in general, but not only on the theoretical aspects of it. Before I close my talk, I would like to thank Jörg Riskamp and Laura Fontanesi, with whom I collaborate closely, and also the Economic Psychology Group and the Decision Neuroscience Group at the University of Basel. And I would like to thank them for their insightful comments on my work. And I would also like to thank Professor Jennifer Trublad and Dr. Xian Lu for being grateful sharing their data with me. And I would like to thank you for your attention.